is so the nuclear transfer work, actually, we have met more challenges than we actually expected. So I know I had a few presentations during this meeting and in other meetings. So I think we probably all very familiar with the technique. And today I just want to spend some time to discuss so-called latest development, but it's more about the challenges we have. So I'm actually going to just take one special real clinical case and to walk you guys through a few slides to explain where we are and what is a challenge and where we are heading to. So we already know the genome can be in any type and can be polar bodies, could be germinal vesicles, could be spindles, could be pronucleus. So any kind of a DNA structure can be transferred from the host cell to, from the donor cells to the host cells. And I presented this case to go through the challenge or some interesting points. And the patient, actually the 35 years old lady, and presented with one pregnancy loss, but then never got pregnant for primary infertility for almost 6 years. And if you look at the first line, by the time they reached our clinic, she went through numerous IVF cycles, and from 21 oocytes, 0 blastocyst formation. And we thought, as any clinician would thought that maybe this patient egg just not suitable for in vitro maturation. And before she came to us, had a couple of fresh embryo transfer with these 3 beautiful 8-cell, 9-cell stage embryo transfer, no pregnancy. Now then she explained to us when we look at her charts, very interesting. She told us, if you wait longer, get my follicle around 22 millimeters. You do retrieval, and half of my eggs, 4 hours after retrieval, become 2 cells, 4 cells. And if we do the retrieval when the follicles are around 16 millimeters, and you trigger for 34 hours with Lupron, Avdro, and you get a bunch of immature eggs. So what would you explain to the patient? Jerry, how can you explain to the patient? She said, my egg, before even meet with sperm, it's already 2 cells, 4 cells. It's a miracle. From the God. So it's a pathogenetic activation. That's what we thought. And this is just summary, she got a huge amount of eggs. Before she presented to us, she already went through 2 IVF cycles. And you can see, it just seems no problem to make it to about the 8-cell stage, but just never go beyond the 8-cell stages. And we suddenly realized maybe she had a meiotic arrest. That's why this egg can be pathogenetically activated. So we started looking into the polar bodies genomes. So here, just before I go further, just to quickly review with everyone about nuclear transfer, particularly polar body transfer. So we all know before fertilization, we have 2 copies of DNA in the polar body and 2 copies in the spindle. We know that. And if there's the sperm intruded, then finish the second meiosis, then the second polar body will have 1 copy of DNA. So this is how normal fertilization. We all know here. Now, since her eggs always can be pathogenetically activated at the polar body stage, so we started suspicious that maybe she never can have a meiosis. So why do we just take the polar body doing the transfer, or take her spindle doing the transfer, because her spindle still have 2 copies. So the idea is take 1 oocyte, take the two parts of genomes, one from the portal body, one from the spindles, and through the nuclear transfer process, hopefully both make it to a new metaphase 2 oocytes, and then we're going to do the egg fertilization. But here it's the same genome, and this will be the different. So then we can fertilize these eggs. I know this part is always a confusion. When I'm in the medical school, always about one end, two ends, and four ends of the genome, and mixed with sponge. Meiosis is always a very interesting part. And actually, our colleagues in China did publish a paper indicating that they can make beautiful euploidy blastocyst embryos from first portal body transfer. So when we carefully look at this patient, the oocytes, and without fertilization, it's always automatically will start to show one per nuclear. And we also believe this per nuclear should be 2 copies, not 1 copy, because they never done the second meiosis. So the idea is that we can do the spindle transfer and the portal body transfer to see if we can produce the normal embryos and to make to the blastocyst stage embryo. So I just want to stop 1 second here. I think we did some internal data analysis, and also our colleagues, Dr. Zukin in Ukraine, that you're always going to see about 3 to 5% of the patients, they went through 3 to 4 good stimulation IVF cycles, and they with good AMH around 4, and you have no trouble to make 15 to 20 eggs. But they just stop all the embryos at a cell stage. And we're going to try, I'm sure you guys try different protocol. You're going to long-term protocol, short-term protocols. Now we realize at least 80% of these patients, they're probably never going to make it to blastocyst. Maybe after 3 IVF cycles, we should start to think about the other options. Either tell them to go for donor eggs and, or looking for different approaches. So this just show we did the nuclear transfer with this patient. This is just summary what I just discussed about this patient. Now, I know it's a very busy slide, but really just need to look at the 2 part. Look at it here. So this is after we did the nuclear transfer, and among the 18 eggs, 6 made it to blastocyst. So this definitely clearly indicates that some factor in the cytoplasma definitely will dictate how the embryo to grow. As a matter of fact, now we understand there's some kind of secret codes to make the blastocyst actually embedded in the cytoplasma. Quite honestly, nothing to do with nuclear genomes. So this patient, as you can see, after several cycles, we managed to make 6 blastocysts and 2 euploidy embryos. And I think there's 1 more coming. Maybe euploidy, we're waiting for the PGS results. Now, also from the gender point of view, the gender is very much balanced, half male, half female. So that just indicated these reconstructed oocytes are not derived from pathogenic activation anymore, because we do see half of the male embryos. We transferred one of these embryos. Unfortunately, it was a chemical pregnancy. So this is an ongoing project. This is just a quick summary, the efficiency of nuclear transfer. This is the first challenge. You can see it's still not very efficient. Among 20 oocytes we started, we got 6 blastocysts. That's not bad. in her case, because she never made it to blastocyst, but if you consider this as a clinical routine, and for the lady give you 28 eggs, you made 2 or 3 eukaryotic embryo, I'm sure they will never come back to you again. So this definitely not reach to the way we want. But micromanipulation, actually, the technique is pretty good. You can see after portal body transfer, we actually can make almost a good 70% of embryo can be successfully reconstructed. So it's just the manipulation seems to have some kind of impact on the quality of the reconstructed eggs, and they seem to have a reduced capability to make to blastocyst as compared with any 35 years old ladies with good stimulation cycles. So how the manipulation affect the quality and early and late embryonic development, that is somewhere we can spend some research on it. We're starting to look into germinal vesicle, which is actually how all the work started way back 20 years ago. Theoretically, with this patient with a meiotic arrest, we can actually start even early going through the germinal vesicle stage. However, germinal vesicle stage, it will be even more challenge. So this is a beautiful germinal vesicle. And this to show how the germinal vesicle transfer. Technically, we accomplished a lot. As a matter of fact, we can make a good reconstruction. But how to have a good germinal vesicle stage cytoplasma, which can support a normal meiotic division and make a normal embryos and create a live birth baby, that's second challenge. This is just a quick look at, I'm sure everybody familiar with this data. As you can see, from the 41 to 42 years, the blastocyst formation around 30, and the eukaryotic embryo is literally around the 7%, but after 43, and this came down. And I'm sure this is our number amount, more than, I don't, it's about 600 patients. So the number pretty reputable. Now, I'm sure each clinic have a very similar picture. As we always say, our patients grow old with us, except as Jerry said, and we're trying to stay young. But the things, when you've been practicing for 5 years, 10 years, you accumulate a lot, but they don't want to give up. So I'm sure all your clinic have the population from 43 to 50 getting higher and higher, and they are not ready to go for donor egg. And this group of patients really, we need help. And apart from our EV groups to doing ovarian rejuvenation and help this group of patients, and we're trying to help from the cellular base, see whether we can improve their quality. And one of the hope still focus on germinal vesicle transfer. So during the last few years, we continue this work to do the germinal vesicle transfer, exchange between the patient and the donor. I'm sure we're all very familiar by now. And then we can do different technique to get egg for that to make the blastocyst. However, the efficiency is still not quite there. This is a quick summary of our last 2 years' work, and we have a good number of germinal vesicle stage oocytes, 43. And as you know, when you want to collect GV, it's not as easy as collecting the mature eggs from 18 millimeter follicles. So sounds like not such a large number, 43 germinal vesicle stage eggs, but it's a huge amount of effort. Again, as I said, almost 60% of the eggs we can successfully reconstruct it. And we also can do many different kind of fancy things. And but in the end, to reach the blastocyst in this particular case, very disappointing. Among the 43 germinal vesicle stages we reconstructed, there's no blastocyst formation. So this is a second challenge in the way to cure or rescue the increased aneuploidy in advanced maternal age. But we think it's going to work. It just needs to have the right approach. But we can definitely go that far, but the very last part is getting very low. So this is a second challenge. Now, we analyze what could be the most common reason. And I think, I'm going to skip these slides. I think there's a slightly difference between the, see if I can explain this concept in 2 minutes. It is slightly different when a patient decides to go donor egg versus a patient going through oocyte rejuvenation or reconstruction with donor eggs. Different, because patients have limited material. They only have 2 eggs. And you somehow have to figure out a way to get these 2 eggs to become 2 blastocysts. When you're going through traditional donor eggs, that's slightly different. You give her 6 eggs, as we said today. It's still a little bit tricky. 6 eggs may not make it to 1 blastocyst. But you can give her another 6 eggs. If financially, if it's not the objective, she can just keep getting the donor egg until she gets the right embryo. But when you do the egg reconstruction, she couldn't give you unlimited supply of her own eggs. So which egg to use to do the reconstruction, we just realized become very important. You can't just pick up all the donor egg, just randomly pick up a donor egg. We know not all the donor eggs are making blastocysts. But when you do the regular donor IVF, it doesn't really matter. You pick up the right one when they become blastocysts. But when you want to use this donor egg to do reconstruction, you kind of have to know the quality of this egg. Because if you pick up the wrong donor eggs, you waste the patient's eggs. So that's the third challenge, how you can figure out the egg is the right egg, which actually have a huge applications for you guys, for all of us. If we have a way to predict this egg going to be produced, you produce blastocysts, you really just need to fertilize the egg, which I'll talk about this morning. Dr. Chapter said maybe we can use the AI system not to recognize the blastocyst stage embryo, but starting from eggs. So we are looking at the 2 approaches. One's looking at the morphology, look at the chromatin. And the study in the mice show that if you show kind of nice chromatin surrounding nucleus, can have a better maturation rate and have a better blastocyst formation rate. So maybe we would like to pick up the germinal vesicle stage egg, which somehow have a good chromatin surrounding. So this is one approach to look at the morphology. As you can see from this picture, that if the germinal vesicle show a poor chromatin surrounding and you have a poor maturation rate. When you have a good surrounding and you have a good maturation rate. So this just shows some more details here. So we can analyze the germinal vesicle. And secondly, we can look at the paravitally space. It seems that show all the embryonal, when the eggs starting to show big paravitally space, tend to be more mature. So in the mice study, and they show that they give a better blastocyst formation rate. So maybe we should look at the morphology. So that's just to summarize that how important it is to find the right germinal vesicle stage egg to match with the patient. Otherwise, we're going to ruin the patient eggs. And this patient usually don't produce that many eggs. So material is very, very limited. So how to find the right donor egg to match is a third challenge. This is a quick summary just to show, I'm not going to go through the details, basically say that with a good morphology GV, you have a better chance to make it to the breast, and even you transfer the poor germinal vesicle GV into the good GV egg, you can have good results. That's what we discussed before. This is just showing the human egg how to differentiate a nice looking germinal vesicle or how to pick the right one, and this is to pick the right one and get a good spindle development. I just want to show, I'm going to skip this. I'm sure we all can tell the different morphology will determine different germinal vesicle stage embryo quad. I want to show just one more here. So germinal vesicle stage embryo egg is very hard to mature, we all know. And another alternative is to go something between the germinal vesicle stage and the metaphase 2 stage. So once the egg starts to go germinal vesicle break down, and we can use this aggregated chromosomes and doing the transfer. And this is a sort of alternative between a real metaphase 2 nuclear transfer, which usually will be too late to rescue the meiotic era, versus germinal vesicle stage. It's extremely challenging still for today. This may be a good alternative, and I think that our colleague, collaborator, Dr. Zukin's group from Ukraine will present some information about clinical outcome in this field. So in conclusion, from the last 2 years of clinical work, we firmly believe that the nuclear transfer reconstruction, or now we call therapeutic reproductive medicine or therapeutic nuclear transfer, has a place in long run in human reproduction. However, still have a long way to go to find the right way to find the right eggs and continue to improve the technique efficiency and improve the quality of the egg after reconstruction is a challenge in front of us. But nevertheless, I think the demand is huge. As I said, the patient population, female, from 42 to 47 increases sharply. And this group of patients, if donor egg is not their option, and this definitely we need to work on it. But good news is for the patient, not due to genetic chromosome error, not due to aneuploidy, but due to genetic defect in the oocytes, which will cause oocytes arrest and embryonic arrest. And this nuclear transfer technique is very efficient, and it can help 3 to 5% of the population who are 30 years or younger with a repeated IVF failure, or even with a euploidy embryo with a repeated miscarriage or implantation failure. Now, of course, Dr. Simon said it could be also other factors, endometritis. But if endometritis was taken away as a factor, then 3 to 5% of patients which never get pregnant from any kind of IVF, they definitely are good candidates for portal body transfer, spindle transfer, or even pronuclear transfer. Also, during the last 2 to 3 years, we accumulated a huge amount of experience even to prove from the genetic point of view and some gene mutation, which contributed to the maturation arrest and the breast system development arrest, which Dr. Zukin could present, I think, later today or tomorrow, have a huge amount of data, which is very exciting to hear. So I will stop my talk for now. Thank you all.
Thank you, Dr. Zhang. Thank you for your beautiful presentation. Are there questions for Dr. Zhang?
Hi. Some of the papers are saying that there may be some imprinting disorder. So what other tests could you do for an embryo besides the PGT analysis and NGS sequencing? Is there any other tests you can do for seeing whether they have imprinting disorder in these embryos?
Very good question. Imprinting, it's always a concern for the safety of our procedure, not even for our procedure, even for the prolonged culture of embryo to blastocyst, and also even for the regular IVF. So this definitely we needed to take into consideration. For now, of course, we're going to follow up with all the live births. So far, I think around the world, how many live births, baby, Dr. Zukin? 13? 13 live births, baby using nuclear transfer. So far, everybody grows, seems fine. But imprinting is important, so we are developing some technique, which with some collaboration. I think in the future, probably we're going to add on more analysis on that, because imprinting is basically the DNA methylation, and I think actually very important once we can find a profile how the normal methylation goes with the normal fertilization. They can apply not just for the nuclear transfer patients, just even for the regular patient goes through prolonged culture like a blastocyst. But I think that's something we're going to add on down the road for all the IVF babies.
Thank you. Thank you very much.
Thanks.
Thank you.